everyone, my name is Lenore Monterrosa and I'm currently a senior and undergraduate research assistant here at the University of Texas at El Paso in El Paso, Texas. And today I want to invite you to come into my lab so that I can show you a little bit of the things I do. My research is in anti-cancer drug discovery, so let's go, let's learn. Hello guys, I'm back. So at UTEP, at the Biological Science Building, we're focusing on different disciplines, but today I want to talk to you about the coolest one, and this one's cancer, which is what I work in. So let's go this way. Besides being a scholar here at the University of Texas at El Paso, I'm also part of RISE, which is the Research Initiative for Scientific Enhancement for Underrepresented Minorities, and I'm lucky to have as my mentor that director of the RISE program. Let's go. In order to maintain safety standards, it is always important for everybody that works at a lab to bring their own ID with them. That's the entrance and the exit. Let's go. So today, I want to talk to you a little bit about what we do here at the Aguilera Lab. We're focusing on anti-cancer drug discovery with the aim to find novel compounds with promising therapeutic activity. And most of all, I want to talk to you about my project. So let's talk about cancer. High-throughput screening of novel compounds is a highly utilized strategy to detect compounds with cytotoxicity activity against cancer cell lines, a continuous endeavor for researchers in the medical chemistry field. Experimental compounds exhibiting selective cytotoxicity on cancer cells and inflicting cell death via apoptosis are preferred as they have less damage and side effects. The specific aim of my project is the following. So we all know that leukemia is a blood cancer, and it starts at the bone marrow. How it works is that an overreproduction of abnormal white blood cells starts to create. Throughout time, after they grow uncontrollably, they tend to outgrow normal blood cells. And with that said, leukemia starts interacting around the human body. It is diagnosed that this year 62,000 new cases will be released. And out of that number, around 25,000 people will die. Therefore, my project focuses on a piperidone, with the main aim to, first of all, find the CC50 value of this piperidone. Now you may be wondering what is the CC50 value. It is defined as a concentration of experimental compound necessary to disturb the integrity of the plasma membrane at 50% of the cell population. Besides that, my other aim was to find the mechanism of action in which this compound was inflicting cell death, either through apoptosis or necrosis. So today, I'm going to guide you through the steps on how to characterize the compound. First, we're going to see how do we work to get the CC50 value out of each compound and understand what it's trying to say. And second, I'm going to try to show you how do we interpret the apoptotic and necrotic states of each compound. But to do that, I need to show you the most important step in our lab, and that is the cell culture. That is due to the fact that we grow different cells. We grow lymphomas, leukemias, breast cancer cells, non-breast cancer cells, ovarian cells, as many as you want. So let's go. However, before we start with this process, safety first. So put on a pair of gloves and come learn. Once we have selected the cells that we're going to use for experimental procedures, it is important to make a plate. I already made one for you guys. So what we're going to do is run a differential nuclear staining assay. This assay is going to give us precise quantification of alive and dead cells in our sample. And by that, we're going to know what cells have been affected by our compound and which ones have not, determining the cell population that's dead. So once we have our plate ready, we have treated with our dyes and our incubation time's ready to read, we bring our sample to the Intel 2000. And this instrument is going to allow us to give us images from 4 different angles of one of our wells. So if we look at this first image, which is the count of all cells, and if we look at the right one, we're only going to see the count of those cells that were actually stained and are alive. This will be our plate, and it will distribute around the camera according to the pattern that we first showed. So once the INSAL 2000 has read our plate and given us a quantification of the images from each well, we're going to come to this instrument, and under the INSAL 2000 workstar, we're going to get exact quantification of the cells that are being that are still alive and the cells that were dead. So if we look at this is the image of if we look at this diagram, we're going to see our plate, and the different colors represent the different levels of cytotoxicity in within each well, always supporting our results on our controls, on our positive and negative controls. And if we look at this side, we're going to see the cells in blue that are alive and in red that are dead. So after we have our CC50 value, our next step is to identify if this compound is inducing apoptosis or necrosis. And a good way to do it is to dosimetry. So what we're going to do is that we're going to look at the 4 different quadrants. The first one representing early apoptosis, the second one late apoptosis, and the final one late necrosis. However, N3 is going to represent viable cells. So today I showed you a little bit of what we do here at this lab, but that's really just the beginning. There's much more that we do, and the best part is that our mentor, Dr. Renato Aguilera, encourages all type of projects and is always pushing us to excel. So guys, thank you for coming and visiting the Aguilera's lab, and always remember that research is like the substrate to our enzyme, and nothing can denature us. Bye guys!